Hello, so this is the final policy analysis for this think tank on cybernetics. Cybernetics with the M100, going from path A to path B, we looked at path integration sciences. So now we're going to go into machine learning, chess programming, and linear classifiers. So what is the importance of this? Why are we looking at cybernetics in a kind of modern sense and taking cybernetics to the next level of augmented space? Controlling our own feedback. That is the coolest concept ever. So we're going to go into building our own customizable feedback, our memory control scheme for customizable feedback. Now, in order to do that, and understanding path integration sciences, in order to go between point A, point B, tech and environmental data, we want to be able to compete against anyone else or any other system that could control or dictate the information that comes into us on any path. So think of it as countering market countering. So we want to be able to go between point A and point B, and we want to be able to say our path, our optimal path. So looking at the optimal path that any device is going to go through in the future, and looking at the environmental condition. So now we're going to create a contiguous system of system approach to developing machine learning linear classifiers and ranking the information from the robotics vision. And from this point forward, I think that the advancement on the M100, the advancement on technology that's going to be mobile computing with cameras, is that the cameras are going to take on their own robotics vision principles for interpreting the environment, whether or not it's specifically through the camera or just machine learning data on filtering any type of known environmental data. Positioning data will be the first and foremost. Anyway, so as we look at this, these two videos that I'm going to show you in this think tank policy scenario here, getting that system of system thinking. So we're going to take a parts system, okay? We're going to take a dichotomy of parts, really specific parts that have shape, that have function, that are specific in their characteristics and metallurgic properties, and so on and so forth. And we're going to build a table that is associative and relevant to how we're going to construct our customizable memory database for feedback. So think of it as a viable system model, and this viable system model is structured from an architectural principle, meaning that it is designed by a set of criteria to reach a functional purpose. So its purpose is ABC, and it's built this way for this problem, and this way for this problem, and this way for this. So it has all these very fundamental rules to break and solve problems by. So we're going to take that system and we're going to use it as our first ordered feedback. Now we're going to take our second ordered and we're going to work through that in machine learning and chess programming as we look at path optimization. So now that we're taking a system of system approach to understanding our path optimization routines, now we're going to be able to have a predictive calculation on positioning moves. So now that we're going into path integration sciences and positioning moves, we're going to be able to say between point A and point B, I predicted all this information flow, I predicted all of this, so therefore I gave this feedback result, and therefore this feedback result gave me this customizable environmental space, and this customized environmental space allowed me to change my memory. Now that augmented memory, that artificial neural network approach to customizing your memory is essentially what we're going to do to combat something. We're going to combat something with that, and we're going to use it in a countermeasure as we think through solving some very complicated problems. So in any event, these two videos here, we're going to work through this first one here. This first one is the finite parts system. So this is the wheel. This is that kind of circularity of reasoning, the wheel of progress. It's taken from a machine used for machine learning algorithms. So there's a very literal machine that's based on machine learning algorithms in solving problems. So we're going to take this wheel, all of its parts, and we're going to assign parts that come from this wheel specifically, because it's at the finite level where we are able to understand and comprehend exactly what an infrastructure is, what a type of thinking is that's contiguous. We can't just manifest randomness and put randomness in there, because randomness doesn't create a continuity that allows us to have structure over the way our memories are formed. We want memories that are formed if we're going to control them, we want memories that are formed around a conceptual framework that is functional. That way we don't lose cohesion. We want contiguous cohesion. And that cohesion is part of a functional paradigm. That functional paradigm is part of how something works. How something works is how something solves a problem, how something works within a boundary, and so on and so forth. So now we're going to take that contiguous system, not just random chaos, and we're going to build a custom artificial neural network for controlling our backpropagation algorithm in order to bring our environmental spaces into a feedback loop of custom memory or custom information on augmented technology, meaning basically our result lines for the information that's going to be extracted and put up and prompted into the augmented technology in the M100. So now that we're going to be able to control that, taking this model, section P is what we're calling it, now we're going to go the next level here as we go into machine learning chess programming. And so this video here is based on a concept of looking at chess programming and machine learning. So we're going through an educational curve of finding linear classifiers and the best way to do that as we look at the different types of machine learning. So path optimization for inductive logic programming, simulated annealing, evolutionary strategies, and neural networks. And from machine learning specifically in this context, we're going to break down chess programming, and this is kind of a conceptual model to do that with. So anyway, cool video. Four-way chess game using these sequences from the animation and putting those sequences based on pawn, king, rook, bishop, and the different chess pieces, and then playing four-way chess. So we're going to use a system of system, meaning that we're taking the screenplay, which is one system of a linguistic or language paradigm and semantics, and then we're going to take that and feed that back into the four-way chess game to play. So we're going to create the system of system loop there. Now that's important to understand, because when we take a system of system loop there that has this type of continuity about it, and then as we take a system of system loop here that has this type of continuity, we get this uniformed continuity about a singular perturbation or singular function. So we're gonna move and iterate all this towards the singular function, and that singular function is the part, the machine, this machine that we're going to look at, and then the machine learning algorithm for this chess programming, and then we're going to bring those two together, and we're going to find the singular function. And this is the coolest part. So I hope that you guys have fun, and I know it's kind of abstract, but abstract thinking really should churn the creative juices and get the think tanks primed in for the philosophy and science side of bringing the best of two worlds together, the science and algorithm teams and the philosophers that really, you know, kick these ideas into full gear. Anyway.